Okay, good morning. So let us continue the lesson. So I will try to give you a little bit of lessons today, but then we also solve some problems from the previous sessions. So do you remember we were talking about the congruency of triangles and then exploring some consequences of those? So the thing that we have learned is that what was the definition of congruency of two triangles? We say that two triangles are congruent if the sides are correspondingly equal and the angles are also correspondingly equal. So in principle we need 6 conditions to be met so that we can say that these two triangles are equal. Yes? But then we realize that we don't need to be very careful about investigating the equality of all 6 pieces. We want to talk about those. First we started with an axiom as usual, or a postulate. So we didn't prove it, we accept that, but that's actually more or less natural. And then today we want to continue our lesson to another one which is not that obvious as before. So we want to prove that if 3 sides of a triangle are correspondingly equal to 3 sides of the other triangle, they have to be congruent. Yes. Of course, from constructive point of view, this is more or less obvious, yes, because there is only one. We can talk about that later, okay? But the point is that we want to talk about this theorem. Theorem. So I call it side-side-side congruency of triangles. Yes. So for example, if I have 2 triangles, it's hard to draw exact copies of 2 triangles here by hand, but let us assume that this is one triangle ABC and this is another triangle. So you need to imagine that these are exactly the same, yes, but of course we don't know it yet. What we know is that we know that AB is equal to A prime B prime. We know that AC is equal to A prime C prime. We know that BC is equal to B prime C prime. Yes. So this is our assumption. We know that. We want to prove that triangle ABC is congruent to triangle A prime B prime C prime. Okay, so this is what we want to prove. Yes. Of course, what we have in our hand is just the previous axiom. So one way that probably seems a little bit natural is to start proving that the angles are equal. Because if I can succeed that 2 angles of this one are equal to 2 angles of the other one, then of course the third angle is automatically equal, and because I already know about equality of sides, then by definition of congruency I can conclude that these are the same.
Wait, check the congruency of 2 triangles. Did we need 2 angles or just 1 angle?
No, I'm just talking about the definition of congruency.
Yeah, but I can't remember.
No, so far we have only one axiom, and that axiom was side, angle, side.
Yeah, so we only need 1 angle or one pair.
Yes, angle. 1 angle. So if we can prove that 1 angle between these 2 are the same, yes, if you want to use the axiom. If you want to use the definition, you have to prove that 2 angles are the same. But of course you are right, it's better to start from the postulate. So I don't know, do you have any idea what we can do? I remember when I would start learning this theorem, it was a little bit strange, but apparently this is the only way if you want to use the axioms. Because, for example, if we succeed to show that this angle A is equal to this angle A prime, then I am done. Yes? Because I know that this side is equal to that side. I know that this side is equal to that side. If I succeed to show, for example, that this angle A also is equal to angle A prime, this problem reduces to SAS congruency theorem, and then I can do that. Yes? So, I don't know, the proof is a little bit strange. Might be you can find another way, but this is the way that I knew it from a long time back. So what we do, I draw a line, a ray, for example, from here, okay, so that this angle be equal to this angle. Yes? And then what I do on this blue ray, I will separate this length here. Okay, so let me see if I can do it more properly. So then this becomes something like that. And then I clean this one. Yes, so and I call this point A double prime. So far, so it's not a very good picture, so yeah, I don't know how much I should try, but so something like this, because these two should also be equal, yes? Because this was already equal to that. If I draw this one equal to this, so this means that in my picture I need to somehow show that these two lines are also the same. So let me call it A double prime. So by construction, I know that this one and that one and that one are equal. These two equal is my assumption. This one is equal to this one is by construction. So this means that these two are also equal. Yes? And then I made this angle equal to that one as well. So if I call this one angle alpha, for example, then this angle is also alpha based on my construction. And then whenever I got this point A double prime, I connected to C prime, and I also connected to A prime. Okay, so now can you tell me why, can you have an argument why these two angles should be the same now? This might be helpful. So let me just put double dash here. BC, according to my assumption, is equal to B prime C prime. Based on construction, A double prime B prime is equal to AB. Based on construction, this angle and that angle match. Yes? So do you see what axiom I have now for this triangle and this upside down triangle? Let me see. They are congruent, yes, because of SAS axiom. So we just write it down. So we say that AB is equal to A double prime B prime, and we know that angle B is equal to angle A double prime B prime C prime, and we know that BC is equal to B prime C prime. So this means that based on SAS side angle side axiom, I can conclude that the triangle ABC is congruent to triangle A double prime B prime C prime. Yes? And then when I conclude this, when I have this, I can make sure that this angle, so let me see, what should I prove? Yes, I prove that A double prime C prime is also equal to AC. Yes. So then I can put 3 dashes here.
Wait.
And 3 dashes here.
Wait, how did you do?
Pardon?
Oh, no, never mind.
You know, we have to prove it. Yes, it's not trivial. But there is another line that I can put 3 dashes on it, yes? Because we know that AC is also equal to A prime C prime. So AC and A prime C prime are also the same. So that's also 3 dashes. Yes? Is that clear? Okay. Now let us give some angles. So let me call this angle beta. If I call this angle beta, what can I call this angle? And why?
Beta.
That's also beta. Why?
Wait. Well, I mean, it's...
Which triangle? So I prime, A prime, B prime, A double prime is an isosceles triangle.
Know that.
Pardon?
How do we know that it's an isosceles? Because they're equal.
No, because I am just following. When I put dashes, they are equal, yes?
Yes, but oh, yeah, of course.
Yeah, that's my construction. So that's beta and that's also beta. Yes? Now tell me, if I give this a name gamma, what can I give this one?
Gamma.
Gamma. Why? Because we just proved it. It was not trivial here. So A prime, C prime, A double prime is an isosceles triangle. By the way, these things that I am talking orally right now, in the exam you have to write them down, yes? Mm-hmm. So you need to mention that A prime, C prime, A double prime is an isosceles triangle because we were able to show that. So if you want, I can continue and now say that, okay, you have told me that AC is equal to A prime, C prime, so I can conclude that A double prime, C prime is also equal to A prime, C prime. That's the reason that this triangle is an isosceles. And then I am done, yes? This shows that this angle is equal to this angle. So you see, this tells me that angle B prime, A prime, C prime is beta plus gamma, and B prime, A double prime, C prime is also beta plus gamma. Yes? So then this means that B prime, A prime, C prime is equal to B prime, A double prime, C prime. Okay, so I was able to show that this angle in total is equal to that angle. Yes? So I am done. Why? Because this triangle is congruent to this triangle. So this angle of this triangle matches with this angle. On the other hand, this angle is equal to this angle. So this means that this total angle here is equal to that one, and that was the goal. Is that understandable? Yes or no?
Yes.
So what we did, we made a copy of this one here. First, by the construction of this method, it's important how you do it, yes? So what I did, I drew a ray here so that this angle matches with that angle, and then on that ray I separated this length and I called it A double prime. So I know that A double prime B prime is indeed equal to AB by my construction. I know that this angle is equal to that angle by my own construction. But I just join A double prime to C prime. There is no guarantee that A double prime C prime is also equal to AC. Yes? This we have to prove. How? We prove that this upside down triangle here and this triangle that I already have are congruent based on SAS postulate. Yes? And then when two triangles are congruent, then I can conclude that A double prime C prime should also be equal to AC. This is one of the consequences that I had. But I already know that AC and A prime C prime are equal. So A double prime C prime is equal to AC. AC itself is equal to A prime C prime. So I have to conclude, I'm able to conclude that A double prime C prime is also equal to A prime C prime. But another consequence of this is that, another consequence that I can conclude from here is that this angle A, this angle B prime, A double prime, C prime, this angle is equal to this angle, BAC, yes? Okay, so keep it here. And then, because these two sides are equal, this narrow triangle that you see here is an isosceles triangle. So if I call this angle beta, this also becomes beta. Yes? And because of this triangle is also an isosceles triangle. So if I call it gamma, this is also gamma. This part is beta, so the total angle is beta plus gamma. The total angle is beta plus gamma. So what I can conclude is that this angle A prime is equal to this angle A double prime. But we also learned that angle A double prime is equal to angle A. So this means that angle A prime is equal to angle A. Okay, so I now know that this angle A and angle A prime are the same. I know that this side is equal to that side. I know that this side is equal to that side. So then it means that these two triangles now are congruent, again, based on SAS axiom. Is that understandable? So we used SAS axiom in two times to be able to prove that if I have three sides from one triangle match with three sides of the other triangle correspondingly, then they are congruent. And that's actually a very important theorem and very effective. Any questions regarding the proof? Yes, is that understand? Yes?
In the beginning, why didn't we just, when you drew the ray, B prime, A prime, double prime, you made it equal to AB, right?
Yes.
That's automatically SAS. Why did we need to do the rest of the stuff? We already...
No, because be careful. This geometry, you have to follow the rules. So what I have in the beginning are equality of three sides. Yes? And I want to prove that these two triangles are congruent. So for congruency, I also need equality of corresponding angles. Is that clear? So it's not yet given. Even though I know three sides of this triangle are the same as three sides of this triangle, we still don't know anything about the angles.
But angle A is the same.
We don't know. We just showed that angle. So you see, the only information that I have are these three pieces. And we don't know anything about if the angles are equal or not. I wanted to show you that if you accept these three, and a consequence of this acceptance is that angles are also equal. And you don't need to be worried about the angles. I don't know, did I answer your question? Yes? So that is very, very important. So you are not allowed to change the order even in this proof. Somehow, there are some little changes that you can do, but the way that I did it, I drew this so that this length becomes equal to that, and this angle becomes equal to that angle. Then I just joined A double prime to C prime. I am joining them. When I am joining, there is no guarantee that what I get is equal to what I have. You understand? So here, I myself make it equal to this one. That is by construction. But then, I get a point, and I had another point here, so I just joined them. When I join them, there is no guarantee that A double prime C prime becomes equal to A prime C prime. Yes, we have to show that. Yes? And how did I show that? I told myself that, okay, B prime C prime is equal to BC, you gave it to me. Alpha, I myself made it equal to this alpha. A double prime B prime, I myself made it equal to that part. And then if you see, you have two sides and the angle between them, with two sides and the angle between them matching correspondingly. Then I can use SAS axiom to conclude that this triangle, upside down triangle, and this triangle are congruent. When they are congruent, there are two immediate consequences of that. One is that A double prime C prime that now I know that A double prime C prime should be equal to AC. Why? Because this upside down triangle is congruent with this one. So the corresponding sides should match. Okay? And then another consequence is that this angle that you see here is equal to this angle. But the problem is not done because I have to show that this red angle is equal to A prime angle. Yes? And then how I did it, then I said that, okay, if I call this one beta and this beta, by my construction, these two sides are equal, so this narrow triangle is an isosceles triangle, so if this part is beta, that part is also beta. Yes? And now we realize that this side is equal to that side, but we already know that this one is also equal to that one. So then this means that this one and this one are also equal. And then this triangle becomes an isosceles triangle again. So if I call this part gamma, I can call this part gamma as well. And then you see that the whole angle here is beta plus gamma. The whole angle here is also beta plus gamma. So this means that this whole angle and that whole angle are equal. But on the other hand, because this triangle is congruent to this one, this and that are the same. So this one is equal to this one is equal to this one, then this means that A prime and A are equal. So it was a little bit convoluted, but that is the only way that more or less we can do it. Is that understandable? Good. So there are some basic constructions. Every now and then I want to talk about them. So if I give you 3 line segments or 3 numbers, how can you construct? I don't know if these are fitting to my... So I don't know. For example, let us consider I have 3 line segments with lengths A, B, and C, and I want to construct a triangle with these sides. So these numbers to be the sides. So that's a construction. It's a very famous construction, but I want you to understand that if you want to draw a triangle whose sides are given, it's a very simple task. Whenever I talk about drawing, you have only 2 instruments in your hand. One of them is the compass, and the other one is just a stick, which is not graduated, yes? It's not calibrated. So just you have a stick, you can just put it next to 2 points and draw a straight line, yes? That is the role of that stick. Okay, how can we do that using this? Yes?
We can start with maybe C.
Yes, so we draw a line like C.
Yeah, and
here.
then we measure with the
Oh, yeah. You put the needle of the compass here, for example, open it up to here.
And then put like one end on once, and then
yes, so you put it here and then open it like that, and then you just do this, yes?
Yeah.
Draw a circle, you don't need to complete the circle.
And then the same with B, but
yeah, we can do the same with B. So from here, so we'd say with B, and then what happens? Whenever they, at a point they intersect, I connect it to here, and I connect it to here. This length is definitely B, and this length is, what was that? It was A, and this length is definitely B. Why? Because this is the center of that circle, yes? And that's the point on the rim of the circle. So its distance to its own center is B, yes? Because I did it myself. So that is a very famous construction. So whenever I give you the sides of a triangle, of course, they should satisfy the inequalities. What was the inequalities? So I need to make sure that, I don't know, one of them is smaller than the sum of the other one and greater than the absolute value of the other two. If these 3 numbers satisfy these double inequality, then we can construct that. Yes? And that is the way that we constructed using the compass and a ruler. Then what was the role of the ruler here is just putting here and connecting these 2 points together. Yes? So that we cannot measure the length, the value for it. Okay. Now I want to think about how we can find the angle bisector of an angle. So I give you, these are the famous constructions. I want you to know them. So I give you an angle here, for example, and then I want you to draw the angle bisector of that using these ancient instruments, compass and not calibrated ruler. Yes. So how can I find this angle bisector? And then you will see that this is related to SSS congruency. Let me tell you something. The constructions, the problems of constructions sometimes appears in Olympiad questions. So you need to be smart to design, to plan something for constructing, and then you have to defend why the method that you introduced actually works. So there are two parts for this problem. First, find any way that you want to construct it, and after that you have to defend it by saying that why, if you follow my recipe, it will give you what you need. That is the essential part. If you just write it down, even if it is correct, probably you will not get the full points because you need to defend why your method works. Yes?
Is that a triangle or just the bisector of any angle?
No, you have an angle, any angle. I give you any angle, and then I ask you to draw the angle bisector of this. You need to present a method, and then you defend why your method works. And these are, I want you to memorize them for this. Let me just not feel ashamed to say memorize this. After understanding, you have to send it to your memory, and then you know that these are famous constructions. Constructing a triangle with given sides is this way, and now we want to go to the second one. Okay, so do you have any suggestions for me? Yes, Rasmus? So let me just draw one angle for you. So let me get rid of these axes here. Okay, I don't know. For example, if I want to draw an angle, but this, I need to give a size, yes? So, okay, let me put 3 points here to make an angle. So here A, I don't know, B, and then let me put a point C here. And to make an angle, I go here, so let me choose rays. So the ray passing from here to here, and the ray passing from here to here. Okay, and now you want to construct the angle bisector here for this angle. Yes? Okay, so if you don't mind, let me just get rid of this, and then let me not show the labels so that we are not confused. I will keep the vertex, but not showing the labels. Okay, now you have your angle and you want to introduce your method. So can you tell me what to do now?
We can begin by just from point A.
Yes.
We just take the compass and draw any
Arbitrary
circle with any radius.
Okay, that's good. By the way, there are some features in GeoGebra that you can ask immediately to draw this angle bisector. But the point is that forget about those features. You want to start from just compass and a not calibrated ruler. So what you said, I take a circle. So I put the needle of the compass here, and as you said, I just draw an arbitrary circle.
Yeah.
Okay. Okay. So let me get rid of this D. I don't know why this works like that. Do you know when I kill D, why this makes this crazy thing?
It just remove that.
Yeah, I want to remove it, but I mean that this should be...
For some, you have the circle tool selected. Okay.
Yeah, that's easier. Okay, now you have your circle here. That was arbitrary, and that is my angle. Then what to do?
Then I think you can just take the compass and put its needle in the two new intersections that we made.
So we need to find the intersections. So in order to be able to use GeoGebra, I need to go to intersect and find the intersection between these two. I got E. And then I go here and find the intersection between these two. I got it like that. Okay. And then you said what to do. This is E, this is F. So what I'm supposed to do?
And then we can just, with our needle out at these two new points, we take the compass and I guess make it some length. I guess we could make it make it the other end touch A.
Yeah, so what you mean in principle, I will take again this circle instruction by my compass and put the needle at E, for example. And I don't know, I draw a circle.
Yeah, I guess it would be best to go to A so that it's has equal length for both our circles.
No, I don't think it is necessary.
Because we would want these two circles to have the same radius, I think.
Okay, I understand what
and then
so it means that the reason it is easier, yes? Okay, so, but what we can do here? So what Rasmus is saying is right, because we are working with GeoGebra, but in principle you really don't need to do that.
Yes.
So that is, so might be that's a better idea if I give you some, I don't know, I go another feature of GeoGebra, circle and center and radius. Okay, so I will give the center. But remember, what do you want to give as radius? For example, let me make it 3. Let us see how 3 works here. Yes. So that is the circle centered at E, and I just randomly chose 3, okay? And then I will do the same thing here. So I will go here, and then I will give you 3. Hopefully they intersect. They don't intersect that much, okay? So let me increase that, okay? Of course they are intersecting as well, but if you don't mind, let me make it 4 from the beginning. So I will choose the center, and then I choose here. Let me make it 4, for example. And then the point is that the next one should also be with the same radius 4. 4 is arbitrary, but they should intersect. Now they are intersecting, yes? So what we do now, find the intersection between these two circles. And then what I need to do is just connect by my ruler. Just I can connect A to H or A to G. Then this is the construction way. But we are claiming that this becomes angle bisector. But we have to defend that. So if you don't mind, let me just connect it to G. Yes, is that understandable? Now we have to defend ourselves that this array that I just drew is the angle bisector of the original angle. So let me just point it out for you. So you see that we can also make it better. So this is the way that we draw the angle bisector. So if you don't mind, let me change the color. I don't know, usually GeoGebra we're used to change the colors automatically. So and then let me also change this. Let me also change this circle to some green, so something like that, and this is also the same thing. Okay, so showing that these two have the same radius. So you see that these two, I don't know, brownish or reddish, whatever it is, they are actually having the same radius, but the center of one of them is E, the center of the other one is F, and then I have the G as the intersection point between these two circles with the same radius and with the same radii and difference. And then I am just joining A to G. I am claiming that this line is indeed the line that I am looking for, and that's the angle bisector. Why is that? Why this isn't the angle bisector?
No.
It comes from side theorem.
Yeah, or if we had drawn are two red circles
Yes.
with the radius so that they touch A perfectly, then we could probably say that if we connected E and F to G, then we would get.
No, but right now you can also do that. So why do you insist to pass it through A? So let us do what Erasmus is saying. So he's saying that, for example, let us connect. So this is the construction finished. But now I want to prove the construction works. So this means that, for example, you can connect E to G, you can connect F to G, yes? And then what do you have? Concentrate on the triangle A, E, G, and A, F, G. And claim is that these two triangles are congruent using side-side theorem. And that is clear, isn't it? So can you tell me here why they are congruent?
Because E, A, and F, A are equal.
Why?
Because
they are radius of the bigger circle.
Yeah.
So they are equal.
And E, G, and F, G are equal.
Why?
They're also the radius of the same circle.
Not the same circle.
But they both have the radius.
Yes, by construction.
Yeah.
And then
they have the same line, AG.
AG in common.
Yeah.
So this triangle AFG with triangle AEG and AFG are congruent because of side theorem. And if they are congruent, it means that the angle here and the angle here, they are actually equal. So the angle EAG and the angle FAG are also equal. Is that clear? So this I want you to remember it in your head. So of course in GeoGebra there is an instruction here. So you go here, you see it's called angle bisector. This is angle bisector. Okay, so if you want to draw the angle bisector, the reason that this is in GeoGebra because it is doable by compass and the ruler. Yes, and this of course you don't need to bother yourself to draw it like this. Of course they have put in a feature, so you go here and that is your angle bisector. So you see GeoGebra drew this one, which matches exactly on the line that we drew. Yes, is that clear? That is a construction that I want you to know. A little bit nicer, okay, so let me just talk a little bit about this. That was also an ancient Greek problem. This is probably natural. They wanted to trisect an angle using the compass and the ruler. And they were working very hard actually to design a way that works all the time. So I give you an angle, and using the compass and the non-calibrated ruler, you are supposed to trisect it, to divide it into 3 equal pieces. It was until the 19th century, I think, mathematicians proved that this is not possible. So it means that you need to throw this idea away that you can do it. Of course, there are some exceptions. For example, if I give you 135 degrees angle, then you can trisect it. How?
45 degrees.
Yes, because 45 degrees we can construct. For example, we will see later, we can construct a right angle triangle with an isosceles one, so 2 angles become 45, 45. So constructing 45 degree angle is actually simple for us. And then 135 divided by 3 becomes 45. So in principle, we can just find and trisect 135 degrees, yes? But if I just randomly give you any angle and I ask you to do it, it turns out that this is impossible. And by the way, if you want to show that something is impossible, it's harder than proving that this is possible, yes? Because when you say it's impossible, you have to have a very smart argument to show that not only us in this generation cannot do it, no one in the future generation, no matter how technology advances, they cannot do it. So that's a very, very big claim. So you need to make sure that the logic is clear. Yes?
So if you have an angle it's sometimes impossible to divide it into 3 equal pieces.
Yeah, just if your tools are only the ancient compass and this non-calibrated rule.
So there's no general way to.
No.
But it's still like physically possible to do. So.
By the way, that's also a good question. Physically means what?
I mean, we could just...
We can measure.
Yeah, just measure the angle.
Yeah, so then, of course, when it comes to measurement, it is not mathematics anymore because it has errors. Because even if you have laser beams, I don't know, and if you want to trisect an angle by measurement, you're still making, some errors. But of course, this is ignorable if you really need them, because you need to see what problem is and how much precision do you really need.
And I mean, really, here you're also going to have error because you're not going to place that needle exactly on the point.
Yeah,
so.
but that's just abstract notions.
Yeah.
Yes. So this is not a line, for example, because this has a thickness. That's not the abstract line is an abstract notion just in your head. Yes. Point. This is not a point, of course. This is more or less a circle. Yes, it's not a point, but these are abstractions. Yes. Anyway, so this I want you to have it in your memory whenever you want, but you don't need to prove them, by the way. If you need, you can say that I draw the angle bisector without proving this. Okay, but it's still you need to know what is the way that you have to do it. Okay. Okay. So now. Okay, there is a little bit more interesting problem, and that is I want you to actually do it before I doing it. I want you to think about it. Okay, so let me just get rid of this. I give you an angle, and I give you a ray. I want you to produce the angle on that ray again. So that is also a nice construction. I want you to learn that. Yes. So what is this? So I give you this angle. For example, I don't have any protractor and anything. I cannot measure the angle. I give you the angle and I give you an arbitrary ray. I don't know. Let me call them. For example, this angle is O. Let me give you this O prime, I don't know, for example, X. It continues forever. And I give you some side for it. For example, I want you to draw another ray on this side so that the angle that you produce is the same size as that angle. Yes? Is the question clear? So I have given you an angle. So let us, for definiteness of discussion, let us everyone do it on the right hand side. Yes, I want you to draw on the right hand side a ray so that after it is done, the measure of this angle is equal to the measure of the given angle. And I want you to learn that this is also possible. So we are exploring consequences of side theorem.
And still using a stick and a compass.
Yes, always. When I say this, it means this.
Okay, the length.
Yes.
Okay.
Yeah.
So
if we have a fixed length, we can open the compass like that.
yeah. Okay.
Yeah.
Okay.
You have the idea? I'm ready to hear. So what should you do? So just because you can draw a ray here, you can draw a ray here. For this purpose of discussion, let us draw the ray here.
Sure. So we can begin with at our angle, or a complete angle. We just draw some line that intersects both of our rays.
Anyway.
Anyway.
Okay.
Yeah. And
so let me call them, for example, A and B.
Sure.
Then?
And then we can begin by copying the length of OB onto our ray. So O prime.
So which one? OA?
No, OB.
OB.
And we make
Yes.
take a compass and mark
we just
same
put
length.
the compass and then we just do it. So yes, you are right. So B prime. So this means that O prime B prime is equal to OB in your construction.
And then we do the same thing with A, but we just draw the circle around O prime that has the same radius as OA.
Oh, okay, so you mean that I open the compass like this, and then put the needle here and draw a circle, yes? So if you do that,
Something like
it
that.
would be something like that,
Yeah.
yes? Yeah.
And then we do the same thing for AB, and we put the needle at B prime with the radius A. The length of AB.
Okay, so you open it like this, and then you put it here. That is very hard for me to do it, to construct it, but I understand what you mean. So you put the needle here, and then you open this length, and then you just draw another circle. So if you don't mind, let me just not complete it, okay? And then you get a point C.
Count A prime.
A prime. Then?
And then we connect O A prime B. Or no,
So you don't
just
need-
O prime A
just-
prime. That's
So
not.
this is a very, very poor picture of mine, of course, but let us see that if we can defend you. And now you are claiming that if this is alpha, this is also alpha.
Yes.
So you need to prove your claim.
So the length of AB, OA, and OB should be exactly equal to the length of O.
Okay, let us just check it one by one. So
Yeah.
you are claiming that so now your method is to prove that these two triangles are congruent.
Yeah.
So O prime B prime is equal to OB by your construction. That's correct. And then B prime A prime, yes, because of the construction, we open the compass to the length of this one. So that is also true that this one is equal to that one. And then, on the other hand, what did we have here? So why O prime A prime is OA? Why is that?
Because we created A prime.
Yeah, because
by
that
the
circle,
radius.
yes, is also, so that's correct. So these two triangles are congruent using this side, side, side.
But couldn't you just, I mean, like A prime could be any point on that circle, right? Like
Yeah, so I mean that is also true, but it is a little bit complicated than necessary, I think. We could do it a little bit simpler, yes?
But no, I mean, it's not, I would say it's not, right? Because, I mean,
Ah, you say that it is not defended.
because how do you know that you picked the right spot on the radius of O prime? I mean, A prime doesn't necessarily have to be O prime A prime doesn't necessarily have to be OA because O prime.
No, because that circle we did in the beginning
Yeah, but we
was
don't.
into the radius of OA.
Yeah, but because I mean A prime O prime A prime is going to be equal to OA, but we don't know that A prime B prime is going to be equal to AB because A prime can be any point on that circle, right? I mean, we don't know exactly what point that is. It is.
No.
No, don't think in that way. So what he's doing, he's actually drawing a circle. So this circle, this poor circle that I have drawn here,
Yeah.
is the center O prime,
Yeah.
and the radius of this is equal to this length.
Yes. That's yeah.
Yes? So if I have any point on this circle,
Yeah.
its distance to O prime is equal to OA.
Yeah.
This is on the one hand.
Yes, that's true.
On the other hand, we put the needle here,
Okay.
and when we open the
Oh yeah. Oh, sorry, I didn't see
this
that.
one as this one.
Yeah, so I
and
didn't
when
see
we
that.
drew another
That
circle.
yeah.
So that's also possible. So that's correct. I mean that this drawing is correct. But any questions here? But that's a very bad picture. But let me just do it a little bit, I think, easier. I don't know if you can call it even easier, but the method is more or less the same. So I have this O angle here, and then I have a ray here, yes?
Yeah, so we can do that.
So what I do, so let me call it O prime. So if I want to do it, what I do is this. I put the needle here and draw a circle, an arbitrary circle here. Yes? I don't need to complete these things. So then it becomes A and B, yes? Okay, so then I will do the same thing here without changing the radius of the compass. I will do the same thing here. So, yes? So I put it here and I also draw it. Something like this. And then I call this point A prime. Yes. And then what I do, I just simply connect these two using my ruler. Yes. Or I can just take and put the needle of the compass here and open it like this, and then put it here and then just do this. Yes. And then I just take this point and connect it here. This angle becomes definitely equal to that angle. Is that right?
Yeah.
That is also correct, but it's a little bit more complicated than this one.
Yes.
But that's the idea, is exactly your idea.
I still don't quite, because I mean, like the radius of B, like of B prime.
Yes.
I mean, could that also be like any size, really? I mean, there are a lot of intersection points for the radius of O prime and B prime, like, right? It doesn't necessarily have to be
Yes, true.
the case.
No, at most two circles can intersect at 2 points. Yes.
No, but I mean, if you, but you can change the size of these radii. I mean, if you, like, if B prime.
Okay. What he is saying is that you need to fine-tune this all the time.
If B prime is
So his criticism is actually correct. His objection, yes, because in the way that you are doing it arbitrarily. Yes. So this means that this length and that length doesn't have anything to do with each other in principle,
No.
as you mentioned, yes? And then if you are lucky, the first choice that we do, they intersect. But if you are unlucky, then these two circles will not intersect.
Well, I mean, you can make them intersect, but
Because it is possible for two circles not to intersect, yes?
Which two circles are we talking about?
This one, so for example, if this length OB is very, very large, what will happen? This length will be very, very large, and then it will contain the previous circle instead of intersecting it.
And will that be a problem?
That's a problem because we will not find that intersection point, but it is not a real big problem because you can fine-tune the length in a different way.
No, but why would that be a problem?
No, because I don't understand why. Because you need an intersection point.
Yeah, but we're not trying. If this circle of O prime B prime is really large,
Yes.
that doesn't really matter because we're not trying to find the intersection with that circle and another circle.
No, if I understood you correctly, so you told me that this arc you see here
Yeah,
is its center B prime,
yeah,
and its radius is BA.
yeah,
Yes,
and
and then that should intersect the previous circle.
yeah,
Otherwise, if I don't have this intersection point, how can I find that?
yeah, and
Okay.
that will always. I don't understand how that could not intersect.
Let us see. If B prime, okay, so
it's relatively fair.
yes, it always intersects. Yes,
Yeah,
but can you prove that it always intersects?
I mean, per definition, if you make it intersect, it will intersect. I mean,
Like-
by construction, it does intersect, as he said.
I mean, we're
No,
placing.
No, that is also part of the proof. So if you have that objection, we should be able to answer
Yeah,
that. We should make sure that this always intersects.
If we're-
In the method that I did, they always intersect, don't they?
I mean,
Because you know that when two circles intersect, if I have two circles like this, they don't intersect. Why? Because if I connect the centers and I call the length OO prime, if OO prime is larger than the sum of two radii, they do not intersect.
oh yes. So then,
And if OO prime is less than the absolute value of R minus R prime, they do not intersect. In this case, the circles are completely outside. In this case, the circles are one inside the other. Yes? So here you see that this is OO prime.
oh yeah.
And
So-
then from here, R minus R prime, if OO prime is less than the difference between these two, they will not intersect, they go inside each other.
Yeah, so for them to not intersect, then O prime B prime would
Yes.
have to be let's see.
So what are the centers?
The
The
centers
centers are, one of them is B prime,
and the other
the
is
other one is O prime.
yeah.
Yes? So O prime, B prime is the distance between two centers.
Yeah.
This should be smaller than the radii of two circles. The radii of the first circle, this one, O prime, A prime,
Yeah.
you took it as OA.
Mhm.
Yes, so it should be less than OA plus. Yes, and the other one is what?
B.
AB.
Yeah.
Yes.
Exactly.
So you need to guarantee that O prime, B prime is less than OA plus AB. Yes?
Yeah.
Is that true or not?
And didn't we like just do this with triangles, proving that?
Exactly. So that is always working. So what
something.
his method is working, yes? Because if this is the case, and of course it should be larger than OA minus OB, minus AB, yes? But this is always the case because this is already a triangle.
Yeah, I'm mixing them up. I keep confusing which point the radius is supposed to intersect with.
Yeah, but that is a good question, by the way. Even in my case, I need to convince myself that this intersection point always appear. But let us discuss about this. Do you agree that we have to check this? If this is the case, Rasmus' method works because we always have the intersection. And why this is correct? Because O prime B prime is equal to the length of OB by his method of construction. So we want to consider, is really O prime B prime smaller than OA plus AB? The answer is yes, because by the method that he described, I have a triangle. If I have a triangle, it means that the triangle inequality in both directions holds. Is that understandable? But that's a good question, because I would say that even in this case, you need to convince yourself that this is working. So this is the way that I actually produce a circle. It's not, I don't need so many things. That's easier. Yes, that's from my point. But that's I think we can really defend this, and it is working. Yes. Okay. Now let me give you another question. If I give you a line, and I give you a point outside, these are fundamental constructions I want you to know. Okay, so if I have a line and I have a point outside, by parallel axiom, we know that there exists a unique line passing through that and parallel to this one. How can you draw that using our ancient equipments? So we want to draw a line that passes through this and is parallel to this one. Based on parallel axiom, we know that such a line exists and it is unique. But the point is, how can we draw them using compass and this? Yes, Afshin?
We can measure the distance from one point and to the point outside.
We cannot measure.
I mean, open the compass.
Okay, so you mean that you just put a random point here?
No, at the end of
Yes, there is no end.
okay, yeah, sure.
So because that line goes forever, there is no end for the point. Yes? Okay, so you just pick a random point here.
Mm-hmm.
So let me call this line L, and let me give this point name A. L and A are given to you, but you told me that I just put a random point here. So let me just call it O. Then?
And then we draw a circle with the radius OA.
With the radius OA. Okay, so if you don't mind, let me make it closer to this so that I can use my fingers. Okay, so you mean that something like that, yes? Okay, so okay, so what you said is this is A, you draw this circle, then what?
And then we find the intersection point of O and the line, circle and the line.
So here
Yeah,
you mean?
there.
For example, I call it B.
Yep, and then we draw another circle with the same radius as circle O, so
Where?
from the center point should be B.
B. Okay, so this means that I open the same amount, and then this time, so it will pass from here, yes?
Yes.
If I do it correctly, and it also, it will go like this. With the same size, then?
And then another circle.
Where?
Like from the intersection point on the line.
Here?
Yeah, there.
C.
With the same radius, OA.
So the same radius, yes? So if that is the case, then what will happen? It will pass through here. Am I right?
Yes.
Yes, it will pass through here.
Oh, okay.
And
Yes.
then we find the intersection point on the circle.
This one.
Yeah.
And then you connect it here.
Yes.
So that is your idea. Okay.
No, A should be the intersection point between the radius of O and B, right?
Yeah, I think so. So you see, this is not the parallel line. I think so. If this is,
No, I think it wouldn't be.
is it? Okay, so let us just do using GeoGebra to see how it works. Okay, that's more precise. So let me just pause and start recording. Okay, so my question is this: I have a line. Yes, this is my line, and I give you a point outside somewhere here. Yes. So your goal is to draw a line that passes through C and is parallel to this line that you see. And I want to follow yours. Yes? So what can I do now?
Any point on the line.
So let me take these away. Show object, show object. So you say that I just choose a point on the line. Yes? So I go here. I choose any point here. Let us make it close to here. So this is D.
And
that is the first thing. Then
a circle with the radius DC and the midpoint D.
Yes.
Yeah. And then intersection point of the circle.
Yes.
With the line.
Yes, I find the intersection point between the circle and the line.
And another circle with center F and radius DC.
Radius DC. Then I don't know how can I make it here. Do you know any feature in GeoGebra?
We want DC, and where should the midpoint be?
So the center should be F, and the radius should be equal to DC.
Not DC.
What?
FC.
FC.
Yes, I think. Yes.
Okay, if in that case it is easy. So then I will just take this one and I just go here.
Yeah, and then another circle, the intersection point of the circle F and the line, and then another circle with midpoint H and length HC.
HC?
Yes.
Then this becomes this circle.
Wait, no. How?
I think you changed your strategy, yes? From the board to GeoGebra.
Oh no, the length should be HF.
Okay.
Yes?
Yes, and then the intersection point between all the circles. And yeah.
This one.
Yeah.
But you see it is not parallel then.
But the line C and I.
It's not parallel, is it?
It doesn't look too parallel.
No?
Okay. Yeah.
So so this is your line,
yeah.
and it is clearly not parallel. So so this is not working here.
I think I might have found a method.
Yes. Yeah, speak louder, please.
I think I might have found a method. I don't know if this works, but I'm just gonna guess it does work. I just drew the radius of.
Okay, so you want to do something like this here?
Yeah.
So if you don't mind, let me just get rid of it. It's easier for me to do it in that way. Okay, so what do you want to do? Okay, so let me just get rid of the axes and I want to get rid of the grids. Okay, and then I draw a line here for you. Okay, so let me just, by the way, make it a little bit odd. Okay, here, and then I give you a point here. This is your point. Okay, can you tell me now what to do?
I'm actually curious if this does work. Okay, so I drew the radius of. Okay, first I drew the radius of any random point on the line.
Okay, so any random point. Do you mind if I just choose A?
Okay,
it's
yeah,
A is a random point. Yes.
So it intersects the point outside.
So may you just tell me again?
So I drew the radius A, so it intersects C.
You mean the circle,
Yeah, the circle.
with center at A,
Yeah.
but passes through C.
Okay.
Yes, this is what you mean.
That's right.
Okay, so
The circle.
so I will take the circle centered at A, passing through C. Okay.
Yeah. Okay, and It doesn't actually, or does it? I wonder. Okay, and then I drew the radius from C. No, I drew the circle centered at C, so it passes through A.
Ah, okay. So I will check this one and then passes through A. This is what you.
No, it doesn't even. No.
Yes.
If we can like make another circle that, like from the intersection point of the circle A and the line with
Yeah.
the same radius as A and C, then maybe we will have
So
another.
can you just this picture is correct? You want to continue with this picture?
No, if we remove the new circle that we drew.
Okay.
Yeah,
Okay. So remove the new circle.
Yes, but somehow make another circle like with the same radius as the circle A,
With
but
this-
on the intersection, midpoint should be the intersection of the circle and the line.
So you mean that I find the intersection between this circle
Yes.
and this line?
Yes.
This
and-
becomes E. Then
But like draw another circle with.
when you say
Draw another circle with the radius AE.
no, where is the center?
E.
Okay. That is also doable.
Yes, and then same. Find the intersection point on the. Wait, let me think.
Because you want to find like another point that's the same distance. That's parallel. That's the same distance. Like that's the distance AC, and also like it's on a straight line on C, so it's parallel.
No,
this is.
Might be these methods will work, I don't know, but I expect you to make it so to not think in this way. In mathematics, you shouldn't start everything from scratch, but you can use the previous construction here. So this random point, I agree.
Can we, if we like connect the line AC?
So let me just go here. Connect. This C is given. The line is given. You pick a random point on this. Let us call it A, and then using your non-calibrated ruler, you can connect these two. Okay, then.
And then now we have an angle between AC.
Exactly.
And then since we can duplicate an angle.
Is that right? Because what Rasmus is saying is that now you don't know the measure of this angle, but you know that this is an angle. And then take this point, we just learned we can reproduce the angle on any ray. Yes? So if this is your ray, you can reproduce, I don't know if I can draw it like this. So this is possible to construct this angle equal in size with this angle. Is that right or not?
Yes.
And then you are done. We don't need to do anything more because by the theorem, if this Z shape, if these two angles are the same, these two lines automatically are parallel. Is that understandable? So in principle, you pick a random point A on the line and connect it to C, and then you do the previous problem on C, and then you are done. Is that right or not? Okay. Another question, if I give you, this is also important, if I give you a line, by the way, that is also a feature in GeoGebra that you can already do that, yeah, so you really don't need to do it, so you just go here, go to the parallel, you see here, and you just click here and just click here, so that is the line that you are supposed to do. But this is doable because of campus and the non-calibrated ruler. Now my question is that, how can you draw a perpendicular line? These are fundamental constructions. How can you make a perpendicular line to a line? So let me just clean everything here. So here I just draw, let us say a line is better, so just a random line here. And if you don't mind, let me get rid of these points. Show object, show object. I just give you a point, any point on the line. Let me just pick this point, C. And can you tell me how can I draw a line that passes through C and is perpendicular to the line? How can I do that? These are fundamental construction, basic constructions that I want you to know, and they are possible.
We can begin by just drawing a circle from C and with any arbitrary length.
Okay, so you just take this tool, any arbitrary length.
Yeah.
Is that okay, for example, here?
It works. And then find intersections.
Intersections. Yes, E and F.
With and then we draw two new circles with points centered at E and F with radius so that they touch C.
Okay, so you mean that I go from E, touches C, and then I do the same thing, touches this.
Then we can draw the line that, or we don't have to do that actually. If we just find all the new intersection points between our new circles.
Yes, so I can do that for you. So you just find this one and that one.
Yeah.
And this one and that one.
But I mean, you don't need two circles. You just draw a line between G and
no, but I don't know what Rasmus is going to do.
And
I'm curious to see.
Now we can draw a circle. If we focus on G and J.
G and J.
We can draw one circle which has its center at G and passes through J, and one circle which has its center.
So we have a lot of circles now. Yes. And then the other one?
And another with the center at J, which passes through G.
Yes.
And now we have...
yes, finally we have it, yes.
We have a circle.
So what you are saying is that now you find the intersection point between these two circles, and you call it K, and then you take K and just connect it with your ruler to C. Yeah. Of course, this is so symmetric that I can guess, but you need to defend yourself why this is the case. Okay? But it is, I think everyone agrees that this is working. Yes, but of course, this is not done yet, because the hard part is that you need to convince the people that your method of construction is actually working.
Yeah.
But there is also a very, very simple possible scenario going on. Try to teach yourself this way. Do not solve everything from scratch. Just refer to the previous problems. So what is a straight line? A straight line is 180 degrees. And you already know how to draw the angle bisector. And when you draw the angle bisector, in this case, it automatically becomes 1990.
Oh, yeah.
Yes? So that method should work. Is that understandable?
Yeah, of course.
So that is easier. So let me just do that. Let us see if it works or not.
Does that method still work when it's 180?
Edit, and I will... Is there any select all? Yes. And then I want to get rid of all of them. Yeah, that's good. So what we do, let us just test it again. So here we have a line, and then I have a point on the line. So let me just keep it A. Okay, so let me just get rid of this, and then I can hopefully move this A a little bit here. Yes. Okay. Now I want to draw this one. Okay. So what you do, you want to make angle bisector. Do you see that? This is an 180 degrees. Yeah. What was the method for the angle bisector? Do you remember? We just draw a circle with some arbitrary radius, and then I find the intersection point between these and that. Yes? And then what do? I will draw another circle. So this time let me choose this, because I want to make sure that the radius are the same. So let me make it, I don't know, 4 this time, and then I will do the same thing here, 4 this time.
Less.
Yes?
Circles.
And then I find the intersection between these two, and then what I just do, I take this and then connect it here. Yes? So I just want, so this doesn't take time, because I just thought that this is the angle bisector of 180 degrees. Yes? What happens if the point is outside? How can you draw a perpendicular line? These are very basic things I want you to learn. Okay, so let me just do the same trick here. So select all, delete. And then this time, I give you a line, but the point is somewhere outside. Okay? And then let me just don't show them to you anymore. The point is to draw a line from C. This is called dropping a perpendicular. You want to drop a perpendicular from C to the line.
No.
I mean, we just learned how to draw parallels. So just draw a parallel line and just do the thing we just did. And then we have a perpendicular.
Oh yeah.
I mean,
Parallel line to what?
Okay, draw a parallel line through C, which we just learned how to do, and then draw a perpendicular, which we just learned how to do.
Because of this problem that we just solved, yes?
Yeah.
So what you are saying is that, let us just use the tool here. So you say that I draw a line parallel to this,
Yeah.
and then this becomes the previous problem, because now the point lies on that line.
Yeah.
Yes? And if I draw a perpendicular line to this, it automatically will be perpendicular to the other one as well. So then I go here, because I already solved this problem, I don't need to explain it. I just click on here, and then this we already know how to do, and then it becomes automatically perpendicular to the other one. So this method of just reducing your problem to a previously solved problem is an extremely important tool in your hand. Do not start solving everything from scratch.
And so if we're in an exam, if it doesn't explicitly say we have to show this, we can just we can always do this because we know how to do it.
Yeah. So the features in GeoGebra, you don't need to explain at all.
No.
So for the time being, we learn perpendicular line, parallel line, perpendicular bisector we will learn, angle bisector we learn, and tangents will also come. So you can just say that if I have a circle, I can draw a tangent line to the circle. But that's also important to know how to draw them. Okay? But everything that we have here more or less is based on the tools that we will learn later. Okay? Okay, and so let us stop here. I want to ask you some problem. That was a nice problem. I was just trying to solve it myself. I found it. And that's exactly at the level that we have it right now. I don't know which one to say. So let me give you this. Yeah, it was a little bit tricky for me in the beginning. You have a square. Let me call it ABCD. And then you pick a random point on DC, wherever you like. A random point. Let me call it point E. So E is a random point on this side of the square, and then you join A to E. And then you draw the angle bisector of this angle. Yes, you draw the angle bisector of this angle, and it will go and hit here. This is, you call it F. So you see, if this is alpha, this is also alpha. We are supposed to show that this is a very nice relation. So if you add DE plus BF, it becomes AE. Yes, I found it very interesting. It's a simple problem, but interesting one. So you see, I just pick a random point E on DC. I connect A to E, and then it makes an angle. I divide it into two parts, and then this green line, which is the angle bisector, goes and cuts BC at F. And then I am claiming that if you measure the size of BF and DE and add them up, it becomes exactly equal to the length of AE.
And this is a square, so all the sides are equal. Yeah.
Not only equal, the angles are also 90 degrees, all four.
But
okay, I think because the time is not enough, I will write another one for you. But next time, there are many problems that we haven't solved. Every time I promise to solve them, but we haven't. I don't know, are you thinking about them or not?
no.
So, there are some problems left from the previous sessions. Next time, I will not teach a new lesson. I want to solve the problems for you. But if you have already solved them, we can actually ask your opinion and just move on. Another problem that I found interesting, that's also good. I have a triangle, a scaling triangle in general, whatever it is, ABC. But of course, this construction is a little bit hard here. So I construct an isosceles triangle on this side. The picture probably will be very poor. This becomes D, so that this side is equal to that side. But not only this one, that is not hard to draw. The other assumption, satisfying the other condition, is hard. And then I make another isosceles triangle here. So that is CE. But not in any case in this way. So that this angle D, this is hard to achieve. I don't know if we really can construct it using our methods. I haven't thought about that. But this assumption is given that this is equal to the angle B of the triangle plus C. This we know. Okay, so these are not just isosceles triangles. So it means that this original triangle is in a way that if you make an isosceles triangle here, an isosceles triangle there, then this angle becomes the sum of these two interior angles. So that's also part of your assumption. Okay? And then what I do, I just connect D to E, and then I draw the median AM. The claim is this: DE is 2 times larger than the median. So we want to prove that DE is 2 times AM. So let me write the assumptions here. So this is an assumption. AD is equal to AB is the assumption. AE equals to AC is the assumption, is an assumption here. And then BM is equal to MC is also an assumption. So based on these assumptions, I want you to prove that this is also the case, that DE is 2 times larger than AM. They are very easy, but I think they have some contest nature problems. Yes, so they are easy, but I think you can find a way. But of course, the hard problem that now I'm thinking is that how can we really draw such a triangle with these properties? Because achieving this goal is not probably that easy. Might be we can also find a way to do it. But I think might be the consequence of this problem will help us to draw such a thing.
Why would it not be easy?
Is it easy? Because because you know that I construct an isosceles triangle,
yeah.
I can have infinitely many possible ones, yes? And then I want to fine-tune it, I mean by drawing. So I mean that I want to find D and E such a way that when I make that triangle, automatically this is satisfied. Is it easy? I don't know. Do you see it's easy?
I mean, I don't see it. I mean, I don't see it as easy. Like I can just do it, but I mean, it doesn't it doesn't seem particularly like, oh, this would be like very difficult. I mean, there was a problem.
No, but drawing things are actually hard in geometry unless you have a concrete. So I mean that in principle, try to use GeoGebra to draw it with all the tools that you have there. Yes,
yeah.
To see that you can do it, you can satisfy all these conditions simultaneously up to here. Because that is of course easy, you just draw that, yes. Okay, so these two problems, I really want you to think about them. They are very, very easy, but I think they have some nature of contest problems at this level. And then next time I really will go back, and there are many problems that I haven't solved, and I always promise to do that. And then we can come to a conclusion. I really want you to hear from you your solutions, and then we can continue. Any questions? Okay, thank you very much. We stop here.